We will be covering chapter 5.2, which is the definite integral. Okay? But before we do that, let's talk about some other stuff. So my first question for you is, if you want to do a Riemann sum, right, and you want accuracy, right, do you want more or less n's? Right? Okay. Reasonably, right? Reasonably, you should say more, right? The reason is because, let's say this is your curve, right? And let's say you're remodeling from like 0 to like 5, right? Two boxes will give you like this, and you're doing a right remon, so it'll go like that. You have this whole area and this whole area, and that's not great because you have stuff sticking over here, stuff missing like right here, bad, right? Okay, but if you had like 5, you'll have like 1, 2, 3, 4, 1, 2, 3, 4, and 5. And then if you like right remon it, you go like that, and then like that, and then like that, and then like that, and then like that, right? Which is like kind of better, right? But the idea is you want more because, you have less weird stuff sticking over, less missing stuff in here, right? Okay. The next question then is, when n increases, what happens to h, right? And let's remember that h is defined as c minus a over n. That is to say, length of interval over number of boxes, right? Reasonably, right? When n increases, n gets bigger, right? C minus a is a constant. We're not changing that, right? So if you have a constant divided by a number and a constant divided by a bigger number, the number gets smaller, right? The output gets smaller. So when n gets bigger, h gets smaller, right? And so my next question is, when n approaches infinity, what happens to h? Like, yes, we know it gets smaller, but towards what value? Or another way to say that is, what is the limit as n approaches infinity of h? And we know that that's the same as saying the limit as n approaches infinity of c minus a, some constant, over h, or sorry, over n. And that should approach 0, right? Imagine like 3 divided by 2 versus 3 divided by 10 versus 3 divided by 1,000, right? Okay. And so now my next question for you is, how would we represent this expanding, increasing of n on, let's say, a right Riemann? Well, work it out and find out. We know that the right Riemann, so let's call it a sub r, is equal to h, right? Width of your boxes, right? Times the sum of the first box, the height of the first box, all the way to the height of the nth box. And you find that height by saying f of a plus kh, right? This gives you the height of each kth box, okay? Well, if you put the limit notation in, right, you say the limit as n approaches infinity of a of, oops, don't know why that happened, of a of r is equal to, well, if you take the limit on the left, you have to do it on the right, right? The limit as n approaches infinity of h times, okay, to n of f of a plus kh. Yeah. Okay, I didn't teach you guys too many of the limit rules, but what I can tell you is you can distribute the limits, right? So this is kind of a trust me bro kind of thing. You can distribute the limits, all right? And if you do that, that is the same as saying the limit as n approaches infinity of h times the limit as n approaches infinity of 1 and f of a plus kh, right? But look, you want n to approach infinity. What you can actually do is you can pop this guy in here because it's a sum, right? In the same way, you can like, let's say like 3 and then like a plus b is the same as 3a plus 3b, right? You can actually just say this is the same as the limit as n approaches infinity of h times, and pay attention to this part, okay? Because we're gonna do a little bit of algebra magic. The limit as n approaches infinity of f of a plus kh, right? But look, we're bringing this inside, and we're saying n is approaching infinity, right? That means we're saying we want an infinite number of n's, which means we want that up there as well, right? And what does this tell us? This is saying, right here, the width of each box is getting impossibly small. Yeah. And this is saying, let's do a different color. This is the corresponding height of each infinitely small box. And you want this here as well because this is written in terms of n. H is equal to c minus a over n. Okay. I would not distribute into there. I would not recommend that. Okay. I would not recommend that. Because nonlinear functions. Okay. You can leave it like this. You don't actually have to know how to do this. Okay. The important part is you understand that we are making tinier and tinier boxes. Okay. So like, let's say, like this is your function, right? From like, let's do color. From here to here, right? You are now taking a bunch of itty bitty tiny little boxes so you can fill it out like that. Da, 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 da. Okay. So you can get the area under the curve. Okay. But if you were to do this, actually, let's put it over here. This is going to be the same as, and I'm going to show you a brand new word. Okay. This is going to be the same as the integral. That's how you read the sign right here. Okay. It's a big tall S, S as in sum. Okay. The integral from A to C, right? Because that's where we're integrating, right? That's what we're kind of summing up from, right? From A to C of your function f of x, right? Let's do f of x in a slightly different color. Let's do it like that. F of x, and we are saying the width of each box, right, Is the width the y value or the x value? The width is the x value, right? Or the difference in x values, right? And thus that gives you f of x dx. It's not times, okay? Not times. I mean, I guess you could view it as times, right? This is saying all of the infinitely tiny y values relative to the x's, okay? This comes from the idea of delta x, right? That whole like f of x plus h minus f of x all over x plus h minus x, and then that gives you h, and h is just the change in x. Yeah, that's all. Okay, that's it. That is how definite integrals work. Yeah, that's it. Thank you for your attention.